Hello, everyone. Thank you for attending today's webinar entitled Break Your Bottlenecks, Optimizing NFV Solutions to Solve Critical Performance Challenges. This webinar is jointly presented by Ixia and 6Wind. My name is Michael Howe. I'm the host of the webinar as well as the first presenter. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We'll try to answer these during the webcast, as well as we'll have some time at the end for Q&A, hopefully. But if more detailed answers are needed or we run out of time, we'll answer them via email. We will capture all the questions. A copy of today's slide deck will be available after the webinar, so please read your follow-up email on instructions for downloading that presentation. As a thank you for attending, a copy of a new and not yet released Ixia white paper entitled Enabling and Testing Network Function Virtualization to Ensure Carrier-Grade Delivery will be sent to your email inbox once it is available. So you can expand your slide area by clicking the Maximize icon on the top right of the slide area or by dragging the bottom corner. And I do recommend that because there's some small text on some of the slides. If you have any technical difficulty, please click on the Help widget as a question mark icon, and it will cover common technical issues. An on-demand version of this webcast will also be available approximately 1 day after this session and will be accessed using the same link that you used to attend this session. So along with me today are Jan Rappaport, a product manager from 6Wind, and Aniket Khosla, a product manager from Ixia. So to go ahead and get started, I'll be covering the first session, which is really an introduction to network function virtualization, and to kind of establish a baseline. So it'll take about 10 minutes to go over that, and I'll turn it over to Jan. So when we think about the motivation and drivers for network function virtualization, this is really driven by the service providers. So we want to kind of look at what they're challenged with and what they're looking to accomplish. So first and foremost, you'll hear from the carriers is the cost of the network. It's a continuous challenge, and the economic model is changing. The CapEx in terms of capital expenditures required to purchase network and equipment, usually on like 5-year cycles where they purchase equipment and they get use of it over time, and then they go in upgrade cycles. And that model is becoming not very effective for the current kind of model we're in here. And this is primarily because network needs are changing more dynamically, and so the model of planning and doing capacity planning for a long period of time and then being able to use that network infrastructure and then upgrade it every 5 years is not meeting the requirements to keep up with the pace of the industry. There's also a high amount of operational expenditures or OpEx costs associated with it. So this is everything related to managing the network. And the more automation, the more things we can do to minimize the touches of each network device from a network engineer or support engineer will help optimize that. So when you look at the model today of appliances used in the network, and when I say the word appliance, it's a very broad term, but it covers things like load balancers and firewalls and BRAS. There's a lot of functions that occur. They are multi-vendor solutions, and these are proprietary platforms. And so there are a lot of effort in terms of evaluating those platforms, testing them, verifying code, deploying them. It's a lot of challenge in terms of maintaining that multi-vendor platform. As well as when you go to deploy an appliance in the network, there are space, power, and cooling requirements for each device. And so that adds up as well, and that adds to the overall OpEx cost as well. So I mentioned capacity planning, and years ago you used to be able to say, we forecast network growth to be at this pace. We can therefore allocate this particular device, and it will meet our needs for 3 to 5 years. That is becoming much more difficult as businesses want the capacity to align with the changing business needs. So when you look at that, the kind of legacy model we have is a little bit broken. As well as with the network, you're going to have things like moves, adds, changes. You have new sites coming online. You have new employees coming online. You have changes to the service requirements in terms of modifying bandwidth. So these things are happening much more dynamically. So what service providers really need to be able to offer is service agility, being able to make these changes and make them very quickly, as well as service elasticity. If a customer's needs are growing rapidly, you want to be able to meet that. If they are shrinking, meaning if something is required for a period of time to expand and then contract after an event is over, for example, they need that service elasticity. So when you look at billable services and actually recognizing revenue for services, there's this measurement of time to revenue. And the average order filled by a carrier takes around 60 days to deliver the service. So while they're deploying the service and trying to actually account revenue for it, there's at least 60 days until a typical service is installed. That's a very long period of time. There's a lot of cancellations that can occur during that period. So they're looking at how do you minimize that time to revenue? How do you minimize that to real-time provisioning of services and maximizing service revenue from the time of enablement of the service, as well as what is the cycle of innovation? How long does it take to deliver new services and value-added services? I think carriers are feeling the pain of the more innovative services being delivered by the over-the-top and cloud providers, and carriers aren't really able to keep up with that. So they want to kind of reduce the overall time to design, develop, test, deploy, and support services. So if they can speed up this cycle of innovation, they'll be adding to the service revenue, as well as when you look at the motivation for network function virtualization, it's an overall, ideally, reduction in network appliance cost. So moving on to the next slide here. So one of the things that everyone's kind of looking at saying, when we look at the cloud and virtualization and the data center, we're realizing a lot of benefits here. We're increasing the how much we're effective use of the hardware, and there's just a tremendous amount of benefits in terms of being virtualized. So just in terms of virtualized server benefit, you can very quickly start and stop virtual machines. You can dynamically change resource allocated to a VM, so you can change memory and CPU. As a comparison, if I was trying to change memory or CPU on a device in the field like a router or a firewall, this would require a truck roll. It would require a downtime to take the machine out of service, installing additional memory and bringing it back up, or a replacement of the device. So current changes to network to resource allocated devices is quite costly. As well as in the virtual space, you can snapshot a VM. So the ability to snapshot can be useful for backup, for copying in terms of replicating. So there's a lot of benefit there. Also, the virtual infrastructure supports live VM migration. So this is taking a virtual machine while running and moving it from one physical server to another physical server. It's a very compelling capability that this infrastructure offers. Also, you have template and image library management. So if I have a template of a router or a template of a firewall, I can roll those out very easily and manage those for consistency. So you have less issues with variations in terms of rolling out canned service offerings. As well as virtualized infrastructures support high availability features and have built-in fault-tolerant features. Just an example of some leaders in server virtualization most folks are probably familiar with is VMware, makes ESXi hypervisor, KVM, QEMU, Citrix makes Zen Server, Microsoft has Hyper-V, which is being integrated into the Windows operating system. So in 2012, 7 carriers got together and formed a working group within the ETSI, which is an ISG for NFV. So this was created in 2012. Shortly after its creation, 13 of those carriers, it had grown to 13 carriers, produced a white paper which provided the vision of what they want out of network function virtualization. Looking at it now, it's grown to over 150 participating companies. So you've seen a big uptick in terms of folks involved, and many of the folks on the line here, companies, are already members or participants in that Etsy ISG. And the broad vision is you take the classical appliance approach, again, appliances like a CDN, a deep packet inspection box, a firewall, a NAT function, and instead of running it on non-commoditized hardware, you're running on vendor-specific appliances, want to make a move towards running these appliances in software, running on standard off-the-shelf server architecture, standard storage, and over a common network infrastructure, and be able to gain the benefit of all the functions virtualization offers, which I was previously mentioning. So this is a really key and critical move, and I think there are things here like core routing and other things that are not part of what is being proposed to be moved. So, is NFV just running on virtualized servers? I just want to bring up the point that it is much more than that. To develop and deploy carrier-grade services, it requires portability, meaning be able to move a function from one server to another. It requires very specific performance and predictable performance, and that's one of the focuses of this session. It requires integrated management and orchestration. It requires, again, elasticity to be able to scale and shrink as needed. There's security requirements, resiliency and network stability, server continuity, operations, energy efficiency, the migration to this technology, and coexistence with existing platforms. So when you think about NFV, it is really much more than just running a function on a virtualized server. And keep in mind, these are carriers who are looking to deliver the 5 nines of service uptime. At a very high level, if you take a look at the Etsy's architecture document, they describe the main components of network function virtualization. So first and foremost, you have the function that's being virtualized, or the virtual network function itself, right? So that's the VNF. Inside of VNF, you may have individual components. So in more recent documents from Etsy, you'll see mention of something called the virtual network function component, because you can have more than one component working together to provide a function. As well as you have element management systems, and then these things are provisioned or deployed on top of a NFV infrastructure. So you'll see this term NFVI. The NFV infrastructure is made up of hardware, which include servers, storage, and the network, a virtualization layer, which is a hypervisor, again, something that's virtualizing the actual server. You'll have virtualization managers. You'll have orchestration. You have VNF managers. You'll have the service and network infrastructure description. And you'll have the overall operations and business system support. So again, it is much more than just taking something like a router or firewall, running it in a virtual server. It's wrapping around all these elements that enable the complete infrastructure or the NFV framework. I have a link there to the Etsy portal. If you navigate to the ISG and NFV, you can look at all the detailed documents. So another very important concept with NFV is something referred to as a network function forwarding graph, or something also commonly referred to as service chaining. And this has to do with the fact that, again, one single function does not make a service. So if I need a load balancer, a firewall, a deep packet inspection device, I may need multiple functions that work together to create a service. And this is, again, referred to as service chaining. And these things can be interconnected through internal links within a server, like through a hypervisor or vSwitch, or can be linked together through external network connections. And again, the underlying network infrastructure is still a key and critical component of building and delivering this service. So let's take a quick look at, if you look at the NFV use cases that the Etsy has published, they're saying, okay, we're talking about virtualization of these functions. What kind of services can be built? So there's a number of use cases that are in this document. Just a quick list is, virtualizing infrastructure as a service, a virtual network function as a service. So again, making these things and wrapping them as services. One example service can be a virtual edge CPE or customer prem router, or a virtual provider edge router. In this screenshot here, what you see is those virtual CPEs would be deployed at various points. It could be deployed in a data center local to the customer. It could be deployed in a common data center. I think that's one of the key and critical components of NFV as you begin to look at this is where are these functions going to be deployed? And if they're in a centralized data center, you'll have the issue of the round trip time to get the data, the packets up to that function and back. So I think this is making a move towards more regional-based data centers, and that not all virtual functions can be deployed in some sort of centralized database or server. Just a quick list of others: virtual network platform, VNF forwarding graphs, the virtualization related to mobile. So this includes the mobile core network and IMS, mobile base stations, virtualization of the home environment, virtualization of content delivery networks, and virtualization of fixed access network functions. So these are some high-level use cases, and many of these are being taken one step further into proof of concepts that are now up and running. I think within NetSea, last count, I think there are 11 proof of concepts that are based on these high-level use cases. So a very common question and something that comes up often is how does NFV compare or contrast with software-defined networking? And just kind of very quickly is that, both NFV and SDN have a goal of deploying services. And these services ideally will be, reducing cost and reducing complexity. So services can be built directly with NFV without SDN, or services can be built with SDN without NFV. So the two can operate completely independently. However, they are very complementary, because if you think about the SDN layer, it's about provisioning the network and talking to the network. And so SDN can be used to provision the network connectivity to interconnect the network functions being deployed. I'm a little late on my content, so I need to move a little faster here. But basically, this would work with the overlay model, which SDN is kind of using tunneling, as well as the underlay model, where SDN is provisioning the paths. Another note is the ONF, which the Open Networking Foundation is leading the charge on in defining the standards for OpenFlow. They now have a memorandum of understanding with the ETSI ISG. They have also produced a white paper talking about how SDN and NFV complement each other. So I think it's very important, and I think my vision or kind of thought is NFV becomes the killer app of SDN, because SDN allows you to provision the network paths. You may want to enlarge your screen on this one, because this one's a little bit difficult to read because the text is small. But in the big picture here, you have servers that are running, that have virtual machines running on them. That's where your functions are going. You're going to have a controller layer, which is where the SDN controllers would sit, that would be able to provision your network paths and connectivity to the virtual network functions. And then you have overall orchestration layer. This could be something like OpenStack or CloudStack. And then you'll have applications and OSS and BSS that sit on top. So a very kind of quick high-level architecture, just showcasing that there are a lot of components that work together to enable NFV. So the topic, again, of this webinar being performance-related, just to set up the next presentation, when you think about performance, there are a few major areas of workload. You have the data plane workload, which is kind of really the moving of the packets, control plane, which is establishment of sessions, if you think of things like BGP and PPP. You have signal processing, which largely is related to the mobile infrastructure. And you have storage, things that are intended to read and write to disk. When you look at the performance impact and potential bottlenecks, you have the server itself. So this includes the processor, the number of cores, the clock rate of that processor, its internal cache capability, the memory channels, the memory latency, the bandwidth of the bus, the instruction set it supports. Another really critical component is large page support and TLB caching. And if these things support deterministic allocation, as well as you have the network interface cards, which allow it to talk to the network Then you have the software design of the function running. Is it leveraging multi-threading? How is it handling memory management? You have the host operating system of the system. This could be VMware. Usually you're running a virtualization layer directly on the hardware. There's the host operating system. You have the impact of the hypervisor itself, and then the network layer within the hypervisor, which could be the Linux bridging or a vSwitch. And then you have the guest OS, or the operating system of the function running on that VM. So one thing I want to quickly point out is a short time ago, the type of performance required was not achievable. But if you look at the innovation in CPU technology, and you even look at Intel's innovation moving towards the next-gen processors and leveraging the data plane development kit, they're achieving packet rates that are very impressive and that can apply to many applications. So again, this isn't replacing core networking. However, when you look at requirements of an edge router, a firewall, a load balancer, it's going to be able to meet these kinds of requirements. So there is a draft document available from the ETSI related to performance and portability. It's an excellent document. Again, it's only in a draft format currently, but it goes a bit deeper into these things. And with these things kind of being mentioned, it's the right time to move on to our second presenter, which is Jan Rappaport. So Jan, product manager from 6Wind, will help identify bottlenecks in these systems and showcase how 6Wind is enabling moving on and overcoming those bottlenecks. Jan?
Thank you, Michael. Hi, everyone. My name is Jan Rappaport. I'm a product manager with 6Wind. And as Michael said, I'm going to explain how a well-designed software architecture can enable high-performance NFV on commercial off-the-shelf hardware by removing the performance bottlenecks of the standard software architecture. So today, we actually see a trend in the industry to move from proprietary hardware platforms with proprietary operating systems and proprietary applications to generic platforms running on general purpose, standard commercial off-the-shelf hardware, running standard operating systems, and from there to virtual environments where applications run in virtual machines totally abstracted from the hardware. As Michael explained, this is enabled by the new multi-core processors from players such as Intel, but also Cavium, Broadcom, or Pilera. But not only, it's also enabled by the ecosystem of the standard Linux operating system and innovative packet processing software that allow to reach performance comparable to ASICs or FPGA-based solutions with the flexibility of software. In the next slides, I'm going to explain the performance bottlenecks that such packet processing software have to address and how 6Wind's 6WindGate software does it, scaling linearly with the number of cores in the system without requiring any change to the existing Linux environment. So typical performance bottlenecks in NFV architecture fall into 4 categories. There is driver level bottlenecks, as standard Intel-based Linux drivers running on the server platform are not designed to receive and send packets at a very high rate. Also, in the virtual switch of the hypervisor running in Linux, you can process around 1 million packets per second per core, and that does not scale when cores are added to the system, reaching a limit of around 6 million packets per second with 10 cores. You add to that the communication bottleneck between the host, the hypervisor, and the virtual machines due to the standard VNIC drivers that have performance bottleneck, that don't have multi-queue support, etc. And finally, inside the virtual machine itself, performance bottlenecks are due to the Linux operating system, and this prevents virtual network functions to operate at the bandwidth they were designed for. So, high-performance networking software for NFV has to take into account these bottlenecks with the right software architecture. This is what 6Wind had in mind when designing the 6WindGate packet processing software. The standard Linux operating system has a lot to deal with apart from pure packet processing. And that's why we have designed a specific packet processing software running on dedicated cores isolated from the Linux operating system. We call this software the FastPath, and it's designed to provide the highest throughput and the lowest latency per core. Packet processing is fully offloaded from the Linux operating system. We support an extensive set of layer 2 to layer 4 networking protocols, including IP forwarding, IPsec, TCP/UDP termination, OVS acceleration, and more. Moreover, this FastPath is transparently synchronized with Linux so that existing Linux applications, management, orchestration systems don't need to be modified. 6-Wingate users continue to use standard Linux configuration tools and benefit from the FastPath packet processing performance. And finally, this packet processing performance scales linearly with the number of cores running the FastPath, so that 6-Wingate users make the most out of today's modern multi-core processor platforms. You have different options to deploy 6-Wingate. We solve the performance bottlenecks either on legacy physical platforms running Linux on commercial off-the-shelf hardware, or inside the Linux of the hypervisor running the virtual switch, as well as inside the virtual machines to provide the same performance as on the physical equipment. In the next slide, we're going to review together some examples of such deployments. The first example is the virtual switch example. 6-Wingate running inside the hypervisor can accelerate the standard virtual switch from openvswitch.org. This is done by offloading packet processing from the Linux OVS data plane to the 6-Wingate FastPath running on dedicated cores. 6-Wingate leverages the Intel DPDK to receive and send packets efficiently and implements its own flow table to get the highest level of performance. And again, this does not require any modification to the standard Linux OVS control plane. In addition, you can combine OVS acceleration with other FastPath protocols such as VXLAN, NAT filtering, IPsec, and more to provide enhanced services at the hypervisor level. And to solve the communication bottleneck between the hypervisor and the virtual machine, 6-Wingate provides a DPDK fast VNIC POLMod driver that gives the highest possible throughput. So we have actually deployed this example, and recently at Open Networking Summit in Santa Clara and NFV and SDN Summit in Paris, we have demonstrated high virtual switching performance. So in this demo, we use a HP DL380P Gen 8 server with dual Intel Xeon processors, each with 10 cores running Red Hat Linux and the standard Open vSwitch, and we use 5 dual-port Mellanox 40 gig NICs. The system is configured using an OpenFlow controller. We start the 6-Wingate binaries on the HP server, and we inject traffic in the system using an Ixia traffic generator loaded with 10 40 gig ports. With this setup, we have demonstrated 195 gigabits of virtual switching performance. So that's the first example of 6-Wingate deployment. Another one is a VNF example. So 6-Wingate running inside a virtual machine to implement a virtual BRAS function. So we have a virtual BRAS acceleration solution that combines the fast VNIC DPDK driver that I talked about previously with the 6-Wingate networking stack inside the virtual machine to offload PPPoE processing from the Linux operating system. Again, this is transparent to the Linux environment so that standard radius DHCP applications in the control plane run unmodified. And with such an architecture, we have demonstrated recently at Mobile World Congress in Barcelona 70 gigabits of PPPoE traffic being processed by 4 virtual BRAS virtual machines, running each on 3 cores of a dual-socket Intel Sandy Bridge platform. There were 256 PPP tunnels established in the system and dynamically added and deleted at a rate of 800 tunnels per second. So these two examples of virtual switch acceleration and VNF acceleration can be combined together to build a complete solution giving the highest NFV packet processing performance. 600 in the hypervisor provides 10 times the Linux virtual switching performance and allows to create unprecedented services by combining OVS acceleration with the rest of the 600 fastpass protocols. Between the hypervisor and the virtual machine, we have the fast VNIC DPDK driver that solves the bottleneck of the communication at that level. And in the virtual machine, we offload packet processing from the Linux operating system and provide an extensive set of protocols to build all kinds of VNF. As I said, the Linux environment is untouched, so that existing Linux applications don't need to be modified. Standard orchestration and automation systems can be used and benefit transparently from the 600 packet processing performance. And so this allows service providers to do a cost-effective transition to NFV. They can build a complete portfolio of virtual network functions combined with accelerated hypervisor to virtualize core functions on commercial off-the-shelf hardware, or move access functions into virtual machines in the core to ease deployment and maintenance, while keeping equivalent performance to physical implementations. Our customers estimate that the combined CapEx and OpEx costs compared to legacy physical equipment are reduced by 75%. So as a conclusion, in this presentation, we have seen how well-designed, efficient packet processing software removes the performance bottlenecks of standard Linux running on commercial off-the-shelf hardware by providing the highest per-core performance, scaling linearly with the number of cores, freeing Linux cores for other processing not related to networking, and this without any need to modify existing Linux applications. This works both in physical and virtual environment, in the virtual switch of the hypervisor, as well as in the VNF itself. 600 typically reaches more than 10 times the performance of a standard Linux, and improving, by the way, the overall stability of the system. So that's it for my slides. I'm giving back the mic to Michael.
Yeah, Jan, thank you very much. I think one takeaway here is we see when we think about cloud technologies, when you require let's say virtualized technologies, a virtualized server, when you request a VM from a cloud, you essentially just require RAM, CPU, storage. You have very few actual performance attributes you can specify. When it comes to running a virtual network function, there are very key and critical things that you can do and leverage in the low layers of the server and hypervisor to improve performance. And I think this is critical for carrier-grade delivery. So to expand more on testing and the products that Ixia offer to facilitate testing of this, I'm going to turn it over to Aniket Khosla, Senior Product Manager at Ixia. Aniket?
Thanks, Mike. Hello, everyone. So what I'm going to do for the next 5 or 10 minutes is kind of go through the set of solutions that Ixia has that can help you with some of the things we've essentially talked about earlier on in this webinar, specifically towards how do you validate and test the performance of your NFV deployments. Okay, to that effect, if you look at Ixia, we traditionally have had an Ixia chassis, which is Ixia's hardware-based traffic generation platform. This has been our bread and butter business, since our inception. For that Ixia chassis, you have specific load modules ranging from 1, 10, 40 to 100 gig. These Ixia load modules are capable of generating very, very high performance and extremely high precision latency measurements. So if you look at the example that essentially Jan just talked about in the previous session, he was using a combination of different load modules running within this Ixia chassis to not just generate high levels of traffic throughput and load, but also in terms of being able to generate high-scale control plane. In addition, we also have a traffic generation and emulation platform called IXVM, which is what I'll spend some of my time kind of talking about today. This IXVM platform should be looked at as Ixia's software-based traffic generation platform. It is essentially all the IP and all the strengths of the Ixia hardware-based traffic generation and emulation platform, but running in a purely software-based environment. This platform is very, very suitable for your development tests, any of your functional tests that you might have in a virtualized environment. This is not to say that the platform is incapable of running at very high loads. It is absolutely capable of running, traffic throughputs in excess of, 1 to 10 gig. But obviously, when it comes to running on a pure software platform, you're not going to be able to have, the nanosecond level latency precisions, if you will, that you have on your hardware platform. So that's essentially the IXVM, platform from the Ixia standpoint. How it essentially works, if you're looking at a very typical, virtualized infrastructure, you're looking at a blade chassis which runs, one or, many blade servers. What you do with this IXVM platform is basically, take the Ixia software, which is IXVM in this particular case, install it on a blade server. That blade server would now have one or more what we call IXVM Linux instances. Those Linux instances can be configured essentially with one or more ports. We have a centralized, IXVM or virtual machine manager or controller, if you will, that essentially talks to your traditional Ixia applications, which I'll talk to in the next slide, IX network and IX load. And you essentially, can run high performance traffic and do your high scale control plane emulation out of these Ixia virtual machines. The major advantage with, our IXVM or software-based platform is the Ixia applications running on the hardware platform and the software platform are exactly the same. So if you have a set of scripts or automation in place that you have today that you're running on your hardware-based platform, you can very easily transition that, for more of your functional tests to a virtual platform. These virtual machines are then capable of, generating high volumes of traffic, running through your virtual switch on your blade server. It can help you characterize the performance of your virtual switch, be it an OBS, an open virtual switch, a tweaked virtual switch with optimizations that you have in place, or any commercially available open switches, if you will. You can now run this traffic not just within the specific blade server, but you can run it across multiple blade servers within your blade chassis, and need be you can run it across multiple blade chassis. In each of these cases, we'll give you a very clear sense of what the performance and scale is, of your blade server, depending upon the provisioning that you essentially have in place on your blade servers and your blade chassis, if you will. So it's a very, very flexible platform. Again, the platform, just to reiterate, our platform is IXVM. It's the Ixia virtual machine emulation, if you will, in terms of traffic generation. Just to quickly recap, what IXVM really is it's purely software based. I want to reiterate the fact that there is no need here for any Ixia proprietary hardware. You can run it on a standard off-the-shelf server, if you will. And the important thing is, as your assets get more and more virtualized, as this discussion has talked about with, the move towards NFV, I think it's going to be increasingly important to have a test tool that can also essentially reside anywhere in your private cloud or even possibly in the public cloud. So IXVM essentially gives you that capability in terms of having a purely virtualized environment, not just in terms of your network functions, but also in, also for a virtualized test port. Like I mentioned, we have two mainstay applications. I'll talk to them in the next couple of slides. IX network and IX load, to be able to, drive these software-based ports. IX network, for those of you who are not aware, is our flagship layer 2-3 test application. Now, this application is essentially responsible for testing the performance and scale of your, your routers, your switches, any BRAS devices that you might have. It supports a whole host of different kinds of protocols, ranging from basic v4, v6 routing to MPLS, to even a number of carrier Ethernet and SDN-related protocols. So, as I mentioned, the application, which is IX network, is essentially the same across the hardware and the virtual platform. So if you know how to use IX network and have a bunch of automation on IX network, that same capability exists for you even on the virtual platform. So the IX network is focused more on the layer 2-3 performance and scale. The other application that we have is IX load. IX load is focused more on being able to do high load generation for applications and security. So things like being able to generate high volumes of HTTP voice, video data, denial of service attacks, things of that nature. IXLoad is the application that you're looking at to drive our software and hardware-based traffic generation and emulation platforms. So this is more focused on applications and security when it comes to being able to test and generate traffic at high loads. Okay, we'll take a look at a couple of an example on how you can test your typical network functions or your virtualized network functions, your VNF. When you're looking at doing tests to validate the performance and scale of your virtual network functions, you can take one of two approaches. In this slide, I'll talk about the one approach that was used essentially by 6WIN, where you're mapping the service to a physical NIC of the server, and you're using traditional Ixia test hardware. So if you look at this example, with an IX network N2X or an IXLoad or breaking point systems, which test layer 2, 3, and layer 4 through 7 services respectively, what you're essentially doing is you're testing the performance and scale of your virtual network functions in a virtualized environment. What this basically lets you do is it lets you compare, it enables you to compare the virtual appliance versus the traditional physical appliance testing in essentially the same way. In both these cases that you're looking at here for layer 2, 3 and layer 4 through 7, you're essentially measuring the same things. You're validating your forwarding performance, your protocol performance, scale, and any kind of multi-dimensional testing where you have a mix of different protocols, a more real-world validation and test, if you will. Okay. The unique aspects of testing such a virtual system, as Mike had mentioned earlier on, in his slides, include everything that could essentially have an impact on the performance. This includes how you've resourced your CPUs, and how much memory do you have, running on your system. Have you over-provisioned the system, in any particular case. So what you also, in a very typical NFV test case scenario, you're looking at, what is my system going to look at when I have events, that are triggered like vMotion, any changes on the fly, is there any true service isolation, things of that nature. So the point I'm making is, you have your traditional way using the Ixia hardware to be able to test VNF functions. More and more we're seeing our customers who are testing, things like VNFs and this move towards NFV is testing in a pure virtual environment. This is typically when you have the Ixia software ports running inside a virtualized infrastructure. There is no Ixia physical hardware, if you will, that's available that is essentially needed to be able to test in this pure software-based environment. So if you look at this classic example, where you have a completely virtual example, a virtual environment, you're looking at the fact that you have your IX VM that's running inside a virtual machine. It connects to a virtual switch, and you can generate high volumes of traffic and control plane emulation to be able to test your VNF and also the performance of your virtual switch. So it's important to understand that you can use IX VM in a pure virtual environment, and there's no need for any physical hardware, if you will. One of the biggest challenges we've seen with our customers. Just a second, having some. One of the most important things our customers are telling us when we're talking to them regarding, testing a virtual network functions or a virtualized infrastructure in general, is when you have a problem in a virtual infrastructure, it becomes pretty difficult to kind of isolate and pinpoint where the problem is. Does the problem lie, with the performance of the server? Is it the performance of the vSwitch? Is it the network that's dropping packets? So, with the recent acquisition of NetOptics by Ixia, we now have a very unique solution in the market that truly differentiates us from any other test tool, and that's the Phantom vTap. It's essentially a virtual tap that essentially, sits. It's a kernel implementation that sits inside your hypervisor and can actually give you a very clear picture of what's going on at the hypervisor level. So, it gives you 100% visibility of inter-virtual machine traffic, if you will, and it's a very, very unique tool that's available, through the Ixia brand right now, through NetOptics, that can essentially really help you isolate and, find problems in your network, when you're running in a purely virtualized infrastructure. This is what truly sets us apart. I encourage you to spend some time, for those of you who are not aware of the Phantom VTAP, to spend some time to see if it can help any of the problems that you guys might be encountering as you move towards the NFV-based solutions. One question that keeps coming up when we talk to a lot of our customers as well, we want to be able to test in a virtual environment. There are a lot of unknowns to us. Can you, kind of articulate some of the benefits to being able to test in a virtual test environment? The one big thing that we tell our customers, and we're also hearing, from a lot of people we talk to, is one of the big benefits of virtualization in general is the ability to quickly snapshot environments or, snapshot virtual machines. So when you're running in a pure virtual environment where it's not just your DUT or your system under test that's virtualized, but so are your test ports, you now have the ability to quickly snapshot problems. So if you have an issue running in a production environment that's, kind of purely virtualized, you have the ability to snapshot that environment, quickly deploy it back into your QA or development environments and, reproduce problems very, very quickly. So when you're looking at an environment that's purely virtualized, I think, by its very nature, virtualization technologies very quickly help you recreate problems that you might be encountering in the field. In addition, because of various orchestration tools that are available, as Mike mentioned, the automation and creation of these managed, layer 2 to 7 networks becomes a lot easier, when you're looking at virtual technologies. So secondly, as Mike had mentioned, earlier on, when you're looking at a purely virtualized environment and you have a service that's, rolled out to one of your customers in a virtual environment, so very often you have to make, changes to the virtual functions. You either need to scale it up, scale it down. You need to make, some security changes, policy changes to your virtualized function. In order to be able to test those, if you have a virtualized environment, including a virtual test port, you can run a lot of those tests or validations remotely without, having to go out through a truck roll. Similarly, when you have problems, in a function that might be deployed at a remote site, for instance, if everything is virtualized, you can instantiate, all your test instances and your virtual network functions remotely, and debug and validate that your configurations and all the changes that you've made to your virtual network function are functioning properly without a truck roll. It's a significant amount of savings, not just in debug times, but also in terms of saving cost. So those are some of the benefits when you're looking at a purely virtualized test environment. The last slide I kind of want to leave you with is when you want to test NFV, what the Ixia solution essentially offers you is the traditional hardware-based platform that we've always had. It's been our bread and butter for a while. In addition, we also have our software-based traffic platform, which I talked about, IXVM. We've had it for about 3 or 4 years, and that platform has matured significantly over the past year and a half, since we're seeing more of our customers wanting to test in pure virtualized environments. So you do have an Ixia hardware and a software platform. That hardware and software platform can help you validate the performance and scale, not just of your physical, but also your virtual infrastructure now. In addition, as I discussed with IXLoad, you have the ability to test the performance of your applications, your storage infrastructure, and even your security. So both the platforms let you test a whole, a vast variety of different, network functions, if you will, using the Ixia tools. And many more. Like I mentioned, you can also test the performance and scale, of your routing instances, if you will, that are virtualized, your server load balancers, firewall, virtual VRASs. And last but not least, the solutions that we have are not just focused specifically on NEMs. We have many equipment manufacturers that are using our solutions to test the performance and scale of their devices. But given the fact that, the NFV has been pushed pretty significantly by the service providers, our software platforms gives us even more strong footing and, holdings, if you will, with the service providers because of the abilities of our software platform and the move towards NFV. Cloud-based users, like I mentioned, in a pure software-based environment, be a private or a public cloud, having a virtualized software port, if you will, traffic generation port for Ixia is extremely critical. So it expands us into, cloud users and enterprise users. So, I'm going to conclude with that. The thought I'll essentially leave you with is when you're looking at testing NFV, we have a host of different solutions, the hardware and the software platforms with different applications that you can use to truly, validate and test the performance and scale of your virtual network functions and your physical and your virtual infrastructure. All right. Thanks, Mike. Back to you.
Thank you very much, Aniket, and thank you to Jan as well. So both the next two presenters did a great job on time management, so I appreciate that. And we do have time for Q&A. So if you haven't yet, you can submit questions by clicking on the Q&A tab. It'll open up a widget, and you can submit a question. So to get started things off with, I thought a great question from a viewer who's saying, have you seen any public examples of such business models which prove NFV's advantages? I think this is a really important question because as we look at, is this technology real? What's going on with it? What we've been seeing is a number of carriers, beginning really last year, have been talking publicly about successful deployments and trials. And I'll just bring up a few that I'm aware of that I've been hearing about at conferences. One is BT has been talking about successfully testing and deploying a virtualized BRAS solution. So I think that's an area where carriers are looking at leveraging NFV because the BRAS appliances are very expensive. So if they can move to NFV for this, it's quite a useful solution. BT has also been talking about their successful deployment of IPsec tunnel termination for Wi-Fi and LTE access services. So again, IPsec tunnel termination is, if you're paying for an expensive gateway to provide that function, and it can be done in a virtual appliance, it'll allow you to scale and apply it effectively. Another BT example was test and deployment of a content distribution network, in that case using Akamai. So I think there's been a number of those. I believe it was also, then there's DT, Deutsche Telekom, who have been publicly talking about their new TerraStream architecture. And one of the areas they deployed it was in Croatia as a trial. It's going quite well, but it's based on NFV and SDN. But it virtualizes DHCP server, IPv4 routing, virtual private networking technology. And so that information is out there. NEC has also been publicly talking about the development of a virtual EPC. So they're saying it's been deployed in several trials. So there's a real examples that are coming out in the market for the mobile market. So I think that the examples and real deployments keep growing. I think if you attend any of the conferences, many of them are adding SDN and NFV to the titles, and you're going to see from the carriers that are really actively moving towards this. And again, if you look through the list of participants, I mean, all the leading carriers in the world are participating. So many are seeing the advantages. Many are testing and trialing these services. So I think they're definitely becoming real world. So moving on the queue here, one of the questions in the queue is asking how 6WIN solutions compare with Wind River. So Jan, would you like to address that one?
Sure, Mike. Thanks. So yes, it's true. We do packet processing software. So I invite you to have a look at the list of protocols that we support and check by yourself. And also, I think one thing very important is that we are not affiliated to any hardware vendor. As you know, Wind River is an Intel subsidiary. And the fact that we are really independent software vendors, for example, lets us support network interface cards that are not Intel, like, for example, the Mellanox 40 gig NICs that we use in our OVS acceleration demo, which are the first 40 gig network interfaces available on the market, or also support for crypto engines that are not Intel crypto engines.
Very interesting. I think Jan brings up a great point, which is, most installed servers have 10 gig NICs, but we clearly see, servers moving towards 40 gig NICs, and Mellanox is one of those vendors that are supporting high-speed NICs. And when you're moving your network interface to that kind of speed, you're going to have to be accelerating the way you handle your packet processing and control plane when moving to NFV. So I think it's a great use case and example there. One question for Aniket related to the Ixious system is, can you describe how IXVM can be used in conjunction with the hardware-based platform?
Sure, absolutely. So again, like I mentioned, because you have the same application that's driving a hardware or a software port, you can actually mix a combination within a single test. So you can have traffic being transmitted by a hardware port and received by a virtual port, or vice versa. Since the applications are almost agnostic of the kind of port that they're running, you can essentially mix them in the same test. It really depends on what you're looking to test. Like I had mentioned, you can run in a pure hardware-based environment, you can run in a pure software-based environment, or you can essentially mix the two. The applications themselves don't really know the difference between a physical and a virtual port. So, you can run them within the same test. Hopefully that answers the question.
Excellent. Thank you, Aniket. Another question for Jan is kind of a technical question. I think it's a great question, which is how would one use 6Wind software on public cloud virtualization platforms? I think it's an interesting question because in many cases when you're even just kicking the tires or trialing network function virtualization, you might just do it purely in the cloud. So in this question, how could I use 6Wind software on any public cloud virtualized platform?
It is a great question indeed. So I try not to go into too technical details. But first of all, as I mentioned during my presentation, first of all, our software is transparent to Linux. So all the existing Linux management tools, orchestration systems, will be able to benefit from our software acceleration. But what is really asked for in this question is how to handle this ecosystem. And so it's true that for the full highest performance solution, you need the full control over the hypervisor, the NIC drivers, and the VM. But we support standard virtual NICs in the VM. So we support VMX3, we support VirtIO, we also support SRIOV and pass-through, obviously, so that if you don't have control on the hypervisor, still you can benefit from 6Wind gate acceleration in the virtual machine. And on the other side, so in the hypervisor, if you have control on the hypervisor but not on the VMs, you would run 6Wind gate in the hypervisor, and our fast VNIC driver in the VM is just a Linux driver that is very straightforward to install, and so that's really common that cloud providers have let's say a little bit tuned Linux distribution for the VMs. So I would say that we have support for the different cases where you control the whole system, VM and hypervisor, but also when you are in a case where you're just running on the VM or just inside the hypervisor.
Excellent. Thank you, Jan. So I think a really interesting question is how are the performance characteristics being defined to ensure consistency and support for NFV? And this is a really interesting question because one of the benchmarks or frameworks of the architecture is portability, meaning if I deploy a virtual network function, I need to be able to move it from one server to another and have consistent performance. So what's in some of the ETSI documents is something known as RAD, Resource Availability Description. And a RAD is a template to define a storage schema for the capabilities of the current resources available, which can be offered by an NFV infrastructure server for the deployment of virtual network functions. So essentially every server would have a RAD template, and it would contain the current capabilities. So what you could envision is in an orchestration, before I go deploying a function or moving a function, I would inquire to determine if the resources available will meet the requirements of what I need. So that is being taken into consideration by the ETSI, and there is some work going on to describe that resource availability. And again, the resource is much more robust than just CPU and memory. It's getting into more specific things to ensure you have the performance required. So I thought that's quite an interesting one. One other question to Jan is related to what does 6Win do to OVS? Could you describe basically understanding how you would modify or work in conjunction with Open vSwitch?
Yes, so actually the answer is simple. What do you modify in Open vSwitch? Nothing. We have transparent synchronization mechanisms so that the fastpath runs in Linux without any change to the Linux applications, and Open vSwitch is one of the Linux applications. So as I said previously, we use standard Linux management tools like IP root, IP tables. In the case of OVS, so you can use OpenFlow, or you can use the OVS CLI to configure the OVS control plane running in Linux. And we have the right mechanisms to transparently synchronize the flows configured in the OVS flow table into the 6Win gate fastpath flow table, so that the system is transparently accelerated.
Excellent. Thank you, Jan. So we are at the top of the hour here, and so I want to let folks know there's been quite a few questions related to the presentation material, recording, and information about IXIA and 6Win products. As you can see on the slide, you can go to www.ixiacom.com for information on IXIA product line. If you put /NFV, it will take you directly to a portal related to network function virtualization. You can also go to www.6win.com. Our email contact is also available, so you can reach out to each one of us directly if you would like. And again, you will be receiving a link to the presentation material. You will also be able to use the same link you clicked for this session to access the recorded session. So you will have access to that by tomorrow, I believe. And then as a thank you, as I mentioned in the opening, we have a white paper coming out from IXIA related to the performance of achieving carrier-grade performance for NFV, and that will be coming out, we're expecting next week. So those of you who've registered will get a link to download that white paper. So we'll go ahead and take a few more questions, but I know folks might need to drop. One of the questions I wanted to answer was related to how can OpenFlow work with NFV service chaining. And so to just backtrack a little bit to one of my slides, is when you think about service chaining, you're essentially connecting network functions that work together to provide an end-to-end service. So one of the most complementary ways SDN can work along with service chaining is by providing the required network connectivity. So SDN can be used to provision paths. So I can talk to network elements such as routers or switches or whatever that supports SDN. I also can talk to things like Open vSwitch or vSwitches that support SDN. And through that, I can provision connectivity, the required network connectivity, so that I have that established end-to-end. So if you think of the dotted line you see in this diagram, that dotted line can be provisioned by SDN. A slightly more complicated example of SDN with service chaining could involve one of the services actually being provided by SDN. So let's say SDN is not just doing pure L2 or L3 connectivity, but let's say you're using SDN to do a distributed firewall. You could have SDN performing one of the services and then your VNF providing another service. So although there's not a lot of, let's say, work or examples of that yet available, it certainly is a possibility to have a service definition that includes services provided directly by the network layer using SDN and functions provided by NFV that are provided by the functions established in the end-to-end path. So hopefully that makes sense. Let me jump through the questions here. So there's one question about how do I find more about 6WIN's FastPath. Jan can comment, and you can definitely go to 6WIN.com, but Jan, specifically around FastPath, what would you provide as feedback?
Yes, so the FastPath is our main technology, so you will easily find that on our website at www.6win.com in the technology area of the website, and also you may find more insights of it on our blog, www.6winblog.com, where you'll find information about the FastPath, but also how it works with the ecosystem, and also thinkings from 6WIN folks about different topics.
Excellent, thanks, Jan. So for the last question, I wanted to answer one related on asking to expand on virtualization of the home environment and asking if there's a proof of concept associated with this. So if you go to the Etsy documents, there's one that is a use case document. Use case number 7 is the virtualization of the home environment. And what they describe is, in a typical home environment, you'll have several devices that might need to be deployed at the end user's equipment, including a routing gateway, a bridge, some sort of modem. So, if you can envision even your home service, a lot of times you'll have one or more devices provided by your carrier. In the proof of concept, in the use case, what they're describing is more of a pure L2 function at the home, and that L2 function is kind of mapping your layer 2 service up to a virtual routing gateway. That virtual routing gateway would provide routing, NAT, DHCP, firewalling type of capabilities. So this use case describes a function where carriers could really minimize the touch out at the home. They provide basic L2 connectivity up to a virtual functions, or a number of functions that are provided using NFV. Now, offhand, I don't know of a POC, but I do know Telstra? No, I believe it's Colt in the UK has an offering where they're doing virtual CPE functions. And I don't know yet if that's for home subscribers or business subscribers, but certainly there are carriers moving towards essentially a virtual customer edge router that, for home use or for business use, and that virtual router sits in a data center or regional POP that is virtualized, and the end connection out to the end subscriber is just a layer 2 connection. So with that, we're several minutes over our allotted time, but we did want to address a number of the questions in the queue. So again, I'd like to thank you for attending, and please look for the follow-up email with the presentation material as well as the white paper. And again, you can use this link again to access the recorded information. Again, thank you to Jan from 6WIN and Aniket from Ixia. We appreciate you guys attending today. Thank you.
Thank you.
Thanks. Bye.